Okay, I had to cut my video off there for a second, but as I was saying, the next thing we can do is the ratio analysis, and the idea is we compare the nth term of our A series to our nth term of our B series, and see if they are greater than, if the result is greater than 1 or less than 1. If A sub n divided by B sub n is greater than 1, then we know that A sub n is larger. And if A sub n divided by B sub n is less than 1, then then B sub n has to be larger. And that makes sense if we just think about how fractions work. So term by term will work, but sometimes you're going to see when you're trying to do homework problems that the term by term stuff is kind of ugly. And I think sometimes it's easier just to think of the ratio between them, because we should be able to compare any nth term and see which one is bigger. And let's just go ahead and check this. So the idea is if I have A sub n over B sub n, well, what is A sub n? So the nth term of A looks like it starts with x's and they're alternating. So -1 to the n minus 1 times x to the a's are normal powers of n. And it looks like the denominator is technically like this first one, for example. This is x to the 1 over 1 factorial. So n factorial. We're going to divide that by b sub n, which is also alternating. But we got to be a little more careful. So b sub n, I added some notation here. Notice that we have, we can add 0 factorial because 0 factorial is 1, 1 factorial is 1, and then the exponents are going up by odd powers 1, 3, 5, 7, 9. So this means that this is going to be n minus 1 factorial, and this is going to be x to the 2n minus 1. It is really important that both the sum of a sub n and the sum of b sub n start with the same n value when comparing, well, not really comparing, when analyzing the ratio. All right, because if I want to know if the nth term of A is larger than the nth term of B, I better make sure that I'm doing the nth term of each. So that's why this n minus 1 factorial is happening in the denominator, because I want to start both with n equals 1, but the first term of B has a 0 in the bottom, so I need to make that n minus 1. So just be really careful about that when you're doing this. And now let's just evaluate it. So what do I actually get? Well, notice right off the bat, my -1s divide out, right? These are going to, that divides out with that. So what I really have here is I have x to the n over n factorial times n minus 1 factorial over x to the 2n minus 1. Now, just a quick note about exponents here. If I say n minus 2n minus 1, that's the same as saying n, or 1, disregard the negative, so 1 minus n is what that simplifies to. And so these are going to simplify to give me x to the 1 minus n. And then what I have in the bottom, well, I have n factorial, which is really n times n minus 1 factorial times n minus 1 factorial. What happens there? Those divide out. And so I am left with x to the 1 minus n over n. Now, here's where we have to be really careful and kind of think about this, because I'm sure you're looking at this right now and you're like, Caleb, why on earth, when the term by term thing worked out so nicely, how on earth is this ratio any help at all? And sometimes the ratio is really clean and it's really definitive. In this case, it's a little ugly, so we just need to think about it critically. If we think about this, remember there's two cases. I'm trying to think what the best way to show this is. If I let n approach infinity, I'm going to do a couple ways to think about this. So if I take the limit as n goes to infinity, what do I have here really? Well, this is going to be equal to, if I have x to the 1 minus n over n, this is going to equal x to the 1 minus infinity over infinity. And remember that x is fixed. Like, I'm just saying for some value of x. So if, like, say x is equal to a half, right? Then I still need to analyze the behavior in terms of n. Because we're saying x near 0, so I'm just pretending x is some arbitrary value. Well, since x, the absolute value of x is less than 1, it's near 0, right? So it's something like 0.01 or something. X to the 1 minus infinity is actually going to be infinity. If you don't see why that is, imagine like 0.01 to the negative infinity, because 1 minus infinity is negative infinity. The negative flips this over from 1/100th to 100 over 1 to the infinity, which is an infinity, because the negative flips the fraction over. And so the top numerator is actually getting really large. And then so is the bottom is infinity as well. This is where we would want to lose L'Hopital's. So if I apply the derivative of the top, oh, and not x. Remember, we're doing everything with respect to n, because x is fixed. What does that equal? Well, the bottom, the derivative of n will be 1, and the top, this is a little hairy. This is the same as saying the derivative of, not x, n, very difficult, of x times x to the negative n. And why am I doing that? Well, x is a constant, so this is really going to equal x times the derivative of x to the negative n. Well, that's really the same as saying the derivative, think of it this way, the derivative of a to the x is equal to a to the x times the ln of a. That's one of our early derivative rules. And so I apply that here to different variables. I have the derivative of x to the n is going to be x to the n, but we keep the negative, times the natural log of n. And then technically we have a chain rule because of that negative exponent, right? This negative exponent, that's a chain rule just waiting to happen. So you have to remember there's a negative 1 in there, all over 1. And I forgot to say that the limit is still there. So I do this all the time. I forget to write the limit. Okay. Okay, so what is happening here? Let's think about this. N is going to infinity. So x is fixed. X is just some number, like a half, you know, or like 0.01. Now, as I just said in this example here, x to the negative n, because x is less than 1, that is actually infinity. And then we have make sure I have all the bits. Oh, and this is ln op, and by my formula here on the left, there's a typo. This should be ln of x. There we go. Notice that my formula over here on the left It's a to the x ln of a. So if my a is x, that should be that. So what is ln of x? Well, again, x is less than 1. So this is some negative number, because like natural log of a half, for example, is a negative number. If you don't believe me, you can check in your calculator. And this is going to be the negative one is there. What happens here? The negatives become positive, and so I have x times some positive number times infinity, which is equal to infinity. And what does that mean? Well, think back to what I said at the beginning. If a sub n divided by b sub n is greater than 1, then a sub n is larger. Infinity is definitely greater than 1. Let me just make sure I say this right. What we're trying to do again, we're trying to show which series is larger. Yeah. So thus we say that a sub n is larger for x near 0. So that would be the ratio analysis. So it is a little complicated there, but I know I said it looks really slick, and you might be thinking, wow, that looks way harder than doing term by term. But sometimes when you set up this ratio, it's like a really nice expression. You'll get something like just x over n, and if x is fixed, then n goes to infinity. Clearly x is, like, clearly that's going to be small. Here we had something funky happening because we have this negative exponent.